Hi everybody, hope you're having a wonderful day. Today we're going to start the equilibrium chapter. So when we talk about equilibrium, we're talking about reversible reactions. So if you remember, reversible reactions are reactions that go forward and also go in reverse. So the reactants react to form products, but then the products also react together to form reactants again. Most reactions in chemistry are reversible, but there are a few that are not. For example, combustion is not a reversible reaction, but most reactions are. So we say that the reaction, when we think it stopped, it didn't really stop. It has reached a dynamic equilibrium. So what is a dynamic equilibrium? That's when opposing reactions, so the forward and the reverse reaction, occur at the same rate. They're happening just as fast as each other. So opposing reactions, the forward and reverse, occur at the same rate. So here is an example of a reversible reaction. If you take hydrogen and iodine, you form hydrogen iodide. Now, hydrogen is a colorless gas. Iodine is purple in color. It's a very, very dark purple solid. It almost looks like it's black, so when it turns into a gas, it's purple in color. It's a deep purple. Then HI is also a colorless gas. So you mix those together and you form this. This is a reversible reaction. So the hydrogen and the iodide react together to form hydrogen iodide, but then the hydrogen iodide dissociates to form hydrogen and iodine back again. Some reactions are kind of easier to tell when you've reached equilibrium. A reaction like this where you have different colors in the reactants and the products, you can kind of tell. Others you can't. You'd have to collect a sample as you go and measure the concentrations of each of your substances to tell whether you've reached equilibrium or not. So initially you would see a color change. The purple would actually get less as you're forming more of your hydrogen iodide, more of your product, but then eventually the color stops changing, and that's when you've reached equilibrium. So that's because the forward rate is equal to the reverse rate. So the rate at which the hydrogen and the iodine combine to form HI is equal to the rate that HI breaks down and forms H2 and I2. So every time you combine these two to form two of those break down to form these two. So let's look at some data that we've collected here. There's the time and the concentrations. We measure concentrations in molarity, of course. And so this is time equals 0. There's the first second, third, and fourth. And you can see that initially we have a lot of your reactants and they decrease over time, but then they become steady. Initially you have no product, but then it increases, and then at equilibrium it becomes steady. So right here, there's where you've reached equilibrium. So if we were to talk about rates, not concentrations, but rates, let's plot what rate would look like in terms of time. So I'm going to start with the forward reaction. And so the forward reaction is our reaction H2 plus I2 yields 2HI. And so that starts out pretty high because all I have is reactants, so they're going to react together. And as time goes by, because I have now less of my reactants, and so it's not going to go as fast. There's going to be less collisions between these to form the HI. So as time goes by, the rate of the forward reaction is going to decrease. It's going to slow down. So the reaction starts pretty fast, and then it slows down. Let's look at the reverse reaction now. So the reverse reaction is when you take the 2HI and you form H2 and I2. So that's going to start at 0. It's going to start very slow because you don't have any products in order, you don't have any of this for this reaction to happen. As time goes by, because you form more and more of this, then you have more collisions of this forming that, and so now your reaction starts increasing in rate, and so it increases and then it remains steady. At equilibrium, there's your equilibrium. That's when the rate of the forward reaction is equal to the rate of the reverse reaction. So your rates will always look like this, where the reverse reaction is increasing and the forward reaction is decreasing. And at equilibrium, they will always be equal to each other. Now, how steep this is or this is, that depends on what type of reaction it is. But the shape, the general shape, will always look the same, and they're always going to be equal to each other at equilibrium. That's in terms of rates. Now let's look at in terms of concentrations. So in terms of concentrations, let's start with my reactants. So reactants, they start pretty high. So my H2 and my I2 are pretty high. And as time goes by, I have less and less of my reactants. It looks like it goes from 5 to 4 to 3 to 1 to 1. And so, let's see, it starts pretty high and then it decreases and then at equilibrium becomes steady. So those are my reactants. Now let's look at the products. Products, of course, start at 0 and they increase as time goes by, and then at equilibrium they're pretty steady. So they start at 0, they increase, and then they become steady at equilibrium. These are my products. Now at equilibrium, the concentration of the products and the reactants are not equal to each other. In this case, the products have a higher concentration than the reactants at equilibrium. So they're not equal to each other, but what is equal is their rates. They remain steady, but they're not equal to each other. Now, this is one instance. There are other possibilities. So you could have your reaction. There's concentration. There's time. So sometimes you will see that, your reactants will always start pretty high and then they decrease. Your products always start pretty low and then they increase and then remain steady. This is also possible. So here, let me label those. There are your products. Here are your reactants. In this case, at equilibrium, this is your equilibrium. You have more reactants than products. In this case, you have more products than reactants. Both could happen. Or sometimes in very rare occasions, it might look like this, where they're both equal to each other. That is very, very rare. That doesn't usually happen. Usually it's either that you have more products at equilibrium or more reactants at equilibrium. The key is the concentrations remain steady. They don't change once you reach equilibrium, but they are not necessarily equal to each other. Only in rare occasions would it be equal. It's the rates that are equal. All right, some requirements for equilibrium. So for a system to say that the equilibrium that the system is at equilibrium, some key things have to happen. First, your system has to be closed, so no extra material goes in, none of your materials leave either. Macroscopic properties are constant. Macro means large, and so large properties are constant at equilibrium. They do not change. So things like concentration. Oops. Or temperature, or pressure, or color. These are macroscopic properties. Those are going to be constant at equilibrium. Number 3, submicroscopic reactions are reversible and occur at equal rates. So the submicroscopic reactions, what's actually happening on a molecular level, is changing. You have a forward reaction, you have a reverse reaction. Those occur at equal rates. They're happening at the same rate. Number 4, they involve gases and aqueous ions only, because those are the ones that change in concentration. If you have a pure solid or a pure liquid, those do not change their concentrations. They have a constant concentration. For example, if you have pure water, there's no such thing as its concentration. It's pure. It doesn't have anything with it. But gases and aqueous substances, you can definitely figure out the concentration, how many particles per unit volume. And then equilibrium shifted by stress, and a new equilibrium system is established as a result. If you remember, this is Le Chatelier's principle, which we'll talk about a little bit later. But basically, if you were to change any of these macroscopic properties, then you've disturbed equilibrium. You're no longer at equilibrium, but the reaction will shift in a way in order to reach a new equilibrium and establish a new equilibrium. Now, how is it that we would know whether we've reached equilibrium or not? You know, in the previous example where we had a color change, maybe we can tell, if you're really good, when the color change stops, and we know that we've reached equilibrium then. However, most reactions, our substances are usually either colorless or white or gray, and they don't really, look like they've changed much. And so how can you tell if you've reached equilibrium? What you could do is you could calculate something called the equilibrium constant. At a given temperature, each reaction has a certain equilibrium constant, or a constant value for an equilibrium expression. Equilibrium constant, in chemistry we use K for constant, and so you could call it just K. You could call it KEQ, EQ for equilibrium, so equilibrium constant. Or you could call it Kc. C stands for concentration. So the constant in terms of concentration. Now, if you have a reaction, A plus B yields C plus D. Sorry, the arrows are in a weird spot there. Where capital letters are your substances, and the lowercase letters are your coefficients when you balance the chemical reaction. K is calculated as concentration of the products multiplied together divided by concentration of the reactants multiplied together, and everything is raised to the power of its coefficient. So how do we calculate that if you actually have a chemical reaction? What you do is you wait until you've reached equilibrium for a known reaction, and then you take a sample of your mixture and you put it into a gas chromatography or a liquid chromatography machine or something like that, and then you measure what the concentrations are, and you multiply them or divide them in this way to calculate K. Now, all of these concentrations are always in terms of molarity, and so they're moles per liter or molar. K is always constant under a set of conditions. So if your pressure and temperature and volume remain the same, then it's going to be a constant, and hence they call it the equilibrium constant. Now, what does K tell us? K tells us what happens at equilibrium in terms of the concentration of the reactants and the products. So if K is the number that's larger than 1, Obviously, K has to be a positive number because your concentrations can be negative. But if it's higher than 1 and you're doing products over reactants, that tells you that the concentration of the products is higher than the concentration of the reactants at equilibrium. And so in that case, when it's larger than 1, that means it's the one that looks like this, where your reactants are less than your products at equilibrium. If K is smaller than 1 and you are doing products over reactants, that means that at equilibrium it looks like this. There are your reactants, here are the products, and so that tells you that you have more reactants than you do products at equilibrium. So that's the significance of K. So the larger K is, the more product favored this reaction is. The more products are going to be at equilibrium. The lower K is, so if K is a really, really small number, that means reactants are favored for this reaction at equilibrium. Remember that when you write the equilibrium expression, that you only include aqueous ions, so aqueous solutions, and gaseous species. You never put liquids or solids in there. There is no concentration of a liquid or solid. So let's write the equilibrium expression for these reactions. Let's start with the first one here. So H2 plus I2 yields 2HI. That was our example from earlier. So you would write, if you want the expression, that means they don't want you to calculate it, they just want the expression. So you say KQ is equal to the concentration of HI, it's your product, raised to the power of its coefficient, so raised to the second power, divided by concentration of your reactants, so H2, raised to the first power, so you don't have to write it in, times concentration of I2, again, raised to the first power, so you don't have to write it in. So that's our equilibrium expression. Let's look at the next one. So if I want the equilibrium expression for this one, I'd say KQ is equal to concentration of my products. I only have one product, which is SO2, raised to the power of its coefficient, it's just raised to the first, divided by my reactants. Now I only include my O2 in my reactants. I do not include the S because it's a solid. So I only include gaseous and aqueous substance. So that's my KQ expression. Let's try the next one. So KQ, and again you can call it just K or KC. Any of these are equivalent. So concentration of my products, so concentration of Ag plus. Now make sure, because Ag plus here, that's an ion, not just solid silver. This is aqueous silver ion. You got to put the plus there. Times the concentration of my other product, Cl minus. Again, you need to include the charge there to indicate that it's an ion. And then divided by, well, my reactant is a solid, so I do not include it. So just divide by 1, or you don't have to put it in there. Let's try another one. KEQ is equal to concentration of my product, so SO3 raised to the power of its coefficient, so raised to the second power, divided by concentration of my reactants. Again, this is a solid, so I ignore it. I do put the oxygen though, so concentration of O2 raised to the power of its coefficient, so raised to the third power. So let's actually try a calculation here. Remember again that whenever we do calculations with Kc, that they need to be in terms of molarity, so moles per liter or mole. So this says determine K at 300 Celsius for the system. N2 plus 3H2 yields 2NH3, so you're making ammonia from hydrogen and nitrogen. And they tell us we have half a mole of nitrogen, 0.3 moles of hydrogen, and 0.18 moles of ammonia in a 2-liter container at equilibrium. So they're telling us that these are the concentrations at equilibrium, and we're trying to find K. In general, whenever you have an equilibrium reaction, or a reaction at equilibrium, the first thing usually that you want to write is your equilibrium expression. So before you calculate the number, just write the expression. So I'm going to write KEQ, or K, whatever you want to call it, is equal to the concentration of the product, so concentration of NH3 raised to the second power divided by the concentration of N2 raised to the first power times the concentration of H2 raised to the third power. Then, if you are trying to find the numerical value for K, which is, in this case, that's what we're looking for, then you plug in your values. Now, they give us moles, and they give us the volume, so we can figure out the molarity of each of my substances. So, concentration of N2 is equal to 0.5 moles divided by 2 liters, so 0.25 molar. Concentration of H2 is 0.3 moles divided by 2 liters, so 0.15 molar. And concentration of NH3 is 0.18 moles divided by 2 liters, so 0.090 molar. So then we plug in our values. So KQ is equal to, concentration of the ammonia is 0.090 molar squared, divided by concentration of N2 is 0.25 molar. Concentration of H2 is 0.15 molar, but then that's cubed. Plug that into your calculator. You end up with 9.6, so that's our answer. Now, what does that 9.6 signify? Well, it's a higher number than 1, so that tells us that this reaction is product favored, meaning that there is more products at equilibrium than there are reactants. So you have at equilibrium, there are more products than reactants. Now, what is the significance of putting that 300 Celsius there? Why do they tell us that it's 300 Celsius? Well, we don't really use it, but that's because if you were to change the temperature, K would have changed. If you were to change the temperature, these numbers would have changed. And so whenever you read an equilibrium constant or you calculate an equilibrium constant, it's for that specific temperature. If you change the temperature, then that number is no longer constant. It actually changes. And in fact, the only thing that changes the equilibrium constant is temperature. All right, let's try a new one. So let's look at the next one. If K at 350 Celsius, again, they're just telling us the temperature just because K would change if you were to change the temperature. So it's this K at this temperature. We have HBr decomposing into H2 and Br2 gases. And they actually give us that K is 0.25. So they're giving us what the equilibrium constant is. This is a number lower than 1, so that tells us there are more reactants than there are products at equilibrium. Anyway, so they give us K, and they give us the equilibrium concentration for HBr is 0.04 molar. We want to find the concentration of hydrogen and bromine gases at equilibrium. So first step, since we're talking about equilibrium here, is write your KQ expression before you do anything else. So let's do that. KQ is equal to the concentration of the products, so H2, times the concentration of Br2, divided by the concentration of the reactants. So concentration of HBr squared. Next, let's try to see what we're solving for. We are trying to solve for the concentration of the H2 and the Br2. And we are given the value for KQ, and we're given the value for the HBr. Now, what do we know about the concentration of H2 and Br2? Well, we don't know what the value is, but we do know that they should be equal to each other. The reason they're equal to each other is because they're products and they're forming when you decompose the HBr. For every 2 HBr's that you decompose, you're going to form one H2 and one Br2. So these concentrations are always going to be the same because they're a 1-to-1 ratio and they're being formed. Initially you have 0 products, and as this decomposes, you're forming for every H2, you're forming one Br2 as well. So it's a 1-to-1 ratio, so you know that these two are equal to each other. Whenever you are trying to solve for concentrations or something like that and you don't know what they are, just say let them be equal to x. So I'm going to say let the concentration of H2 equal x. That means the concentration of Br2 is also going to be x because they're a 1-to-1. So now I'm going to plug in my values. So KEQ is equal to x times x divided by, they tell us HBr is 0.04 molar. And they also give us the value for KQ. KQ is 0.250. So I know that x times x divided by 0.04 is equal to 0.25. So that means x squared over 0.04 equals 0.25. If I multiply those two numbers, I'll get what x squared is equal to, and then I can take the square root. So then if you solve for x, get that x is equal to 0.02 mole, which is my concentration of H2 and my concentration of Br2. So that's my answer. All right, that's it for today. Hope you have a wonderful rest of your day.